Okie dokie. Welcome to, I don't know what number we're on, but it's the second low-level runtime Legion School session. So let's see, last time we talked, we looked at the high level about how we expose everything to high-level runtime and applications as these handles, and how we have to look up internal pointers in Realm for the implementations of these things, and how we do that in a way where, in the common case, we don't have to take any locks, since commonly we'll be looking up these things on lots of threads in parallel. We then spent a little bit of time looking at events as the first thing, and how there's actually at the application level, there's three different kinds of events. There's Realm internal events, there's user events, which are triggered by the application, and then there are barriers, which have a lot in common with events, but enough different that behind the scenes in the implementation, there's actually two different implementations. One is the generational event implementation, and a different one that's the barrier implementation. So I was thinking today we would dig into the implementation of generational events, and then use that to lead into how we do distributed data structures and active messages and GasNet and stuff like that. So folks should interrupt whenever they need to. We are going to jump into, let's see, where should we start? Why don't we start in, why don't we actually just start at the top again? We'll start with low-level.h and look at the event definition, and then go to the implementation, and then go to the implementation of the implementation. So class event. So if we remember here, it is basically events have an ID. Remember, every handle in Realm is this ID type, but then events have an additional field, this generation field, which is how we are able to overlay many events onto the same data structure, and as a result, we don't have to worry about we don't have to worry about reclaiming events, because we're able to simply reuse an existing one. We have a number of methods on events. The ones that'll be most interesting right now are the has triggered one, which is how you test whether something is triggered, and wait, which is how, as an application, you can block a thread, or you can suspend your execution on until an event returns. And as we'll see, most commonly what we do on the inside, though, is we will register activities as being dependent on events, and do it in a way that doesn't involve any threads actually having to block. So since this is meant to be a generic wrapper, we have this implementation function, which is going to be used inside the runtime. We'll implement all the actual guts of an event in this impl subclass, and this is our entry point. It looks up our ID in that dynamic tree data structure, dynamic table data structure, sorry, and gives us an impl star. So let's go look at what the impl star is, and that will be in low-level impl.h. And I think I mentioned this last time, but a bunch of these things are actually in a fair amount of flux because of changes to resilience that are coming up. But if you understand how this stuff works now, it'll be much easier to see how it was changed in the resilience version. Okay, so let's go find event impl. So again, remember, so event impl, since there's two different kinds of implementations, we have the generational events and the barriers, which are both of them have the property that you can test whether they've triggered, and you can wait on them. And so here's those two external entry points, the has triggered and the external wait. And then, as I said, the main one we actually use internally is this idea of adding a waiter to an event. And so this is more of a callback-based mechanism where you can say what generation you're waiting for, and you register a little callback object, an event waiter object, which we'll look at in a moment. And that's used to basically trigger other actions, wake up other actions when the event they were had as a precondition is complete. So event impl is a pure virtual interface. What we actually want to look at is this gen event impl, which is the implementation for generational events. And it's going to have implementations for has triggered, external wait, and add waiter. It's also going to have an implementation for actually triggering. So triggering is something you can do with a generational event, as opposed to a barrier we'll probably see next time, works differently. And then there's a couple other methods here which we will talk about how they're used. But why don't we dig into how generational events get created and how they get tested and used. So I guess we should look at the implementation, the data structure for this. For a generational event starts with knowing what its handle is, the ID. And since this is a generational, the events themselves store a generation, but a generational event is all the generations. So instead of having a whole event data structure, it actually just has the ID. We keep track of who the owner is. This is which node in the distributed runtime owns the event. And the rule for an event is that whatever node creates an event is always the owner for an event. So actually, technically, this owner could be always derived from pulling a few bits out of the ID, but we cache it because we use it so often. We need a couple other things to track the current state of the event. Generation is how many generations are known to have triggered. And this can actually be different on different nodes because we don't always send messages right away when an event triggers. And as we'll see, the way remote nodes hear about changes to the generation is by issuing subscriptions. And there's no point in subscribing to something you already subscribed to. So remote versions of an event will also keep track of what generation they subscribe to try to eliminate some messages. This next free field here is actually part of the dynamic table property functionality. Basically, when since we can reuse generational events once they've triggered, we keep a free list and we actually explicitly thread the list through our event, so we don't have to build other data structures. So that's used by the dynamic table stuff. We also have a mutex, which we'll use to access internal data. And in particular, the internal data we have is if you are the owner node, we keep track of what other nodes have subscribed to this event. And so that's our remote waiters. And then we also keep a list of basically local callbacks to call when this event triggers. And so that's a vector of event waiters, and that's the local waiter count. Okay, so that's our basic data structure, and now we're going to have to basically there's 4 or 5 different things that can occur to events, and we need to make sure that all these things get updated consistently. One thing you'll see though is again, and like I said, this is going to be a recurring theme. We'll do a number of tests when possible to try to have common cases proceed without ever having to take a lock. So although every gen event impl has its own mutex for protecting its data structures, we'll have monotonicity properties, in particular with the generation field, that allow us to do sound tests for triggeredness generally that can be done without taking the mutex, and only if that test fails do we take the mutex and do the precise check. Okay. So that's that. Let's go into lowlevel.cc. And again, this is the kitchen sink of pretty much all the non-GPU realm stuff right now. I am in the process of basically pulling this out into separate files, but that hasn't hit the master branch yet. So let's go find gen event impl in here. Let's first look at create event, create generational event. You'll see this gets used an awful lot inside the runtime. Basically, whenever a new operation is requested of Realm, we'll almost always create a new generational event that will be the finish event for that operation. And so you'll see create gen event get called in lots of places. If you create a user event from the application level, that's also just a generational event. And somewhere around here. Okay, so here's where we create the generational event. And it's not too bad. This is the local event free list is part of our dynamic table data structure. And so this call here basically says, get me the first entry on the list, but it also knows how to create new entries on the list if there aren't any available. So basically the list actually starts out empty. And then if you ask for an event and the list is empty, then what we do is we actually just populate the next leaf node in our dynamic table tree and put all the entries on that block into the free list and then just try again. So we go get a generational event that's known to be available. I guess we assert that it's valid. We assert that its ID is correct. Basically, they're just sanity checks that the dynamic table code is working. Logging, there's lots of logging related to events, since these are the glue that holds everything in Realm together. Quite often when someone gets stuck, the first place to look is use these event logging messages to basically regenerate the event graph. There's also some tracing that's used for the tracking dependencies between high-level stuff. I can't remember, is this Legion Spy or Legion Prof or all of the above? Okay, but anyway, what comes back from this is a generational event impl. So when you want to create a new event, quite often actually what create gen event means is reuse existing gen event, and we send back a pointer to it. If I search backwards, whoa, that was not what I wanted. I do that more precisely. There we go. If we go look at where this is used, quite often, after we call a gen event, actually the thing we do is we try to convert that back into an event. And like I said, the event handles that we give back have a particular generation. And so if you create a generational event, you can ask for basically an event handle that captures the current event. And this construct is always safe to do because create generational event is always going to create an event owned by the current node, which means, as we see, the generation field in there is always precise. And so current event is basically just going to build a handle that uses the ID and the generation field in the gen event impl to build a handle that describes the current event. The owner of an event is never actually, technically, there is one case that we'll see where it can actually be slightly behind the times in terms of what generations are triggered, but it's almost always caught up. And in particular, you cannot reuse a generational event unless the owner has caught up. So this construct here that you'll see a lot of times is a safe thing to do. Okay, so that was creating a generational event. Let's look next at the case for asking whether an event has triggered. So actually, let's jump real quick over to event has triggered, and we'll see how we get in here. So event has triggered is pretty simple. We take the ID field that's part of our event and use that to get back the impl, and then we call the gen event impls has triggered. But again, remember, because the generational event impl describes all the generations, this is where we have to take the generation field from the event handle and pass it in as an argument. And so whereas all the event handles have the generation implicit, all the methods on a gen event impl actually take an explicit generation. So with that little detour, let's go back to gen event impl has triggered. Okay, so this is a test to see whether an event has triggered. It is an inherently racy thing to do. I mean, basically, generation events can only go from untriggered to triggered. So basically, if you call has triggered and you get back a true, then definitely the event is triggered. But if you get back a false, that doesn't necessarily mean the event didn't trigger while that false was being returned to you. And so since has triggered is an inherently racy thing to do, it turns out that we don't ever have to take a mutex at all. In fact, all we have to do is we look at that generation field and we ask whether the generation that we're asking about is less than or equal to the number of generations that are known to have triggered. And so this relies on the monotonicity property I said. Basically, we know the generation field can only increase over time. And so if we look at it without taking a lock and we see that it is large enough, then it will always be large enough in the future, and returning true from this is a safe thing to do. If it's not currently large enough, then it may mean that somebody may be at this moment making it, triggering that version. And in that case, there will return false, but it's always a race condition anyway. So we don't worry about that case. And so as what you'll see is that many cases where we do this, has triggered is almost always just an early out for doing something else that involves actually adding a waiter specifically to a generation. So the good news here is this is quick. Again, we have some more tracing code to basically infer dependencies between things. But the actual functionality is just this one test right here. And in particular, it's lock free. Okay, so that was has triggered. Now let's look at external wait, which is if you actually want a thread to block on an event. then this is what you do. And so this is not the encouraged way to do it, but it does show the basic idea of creating waiters. So I'll show you how that works. So this is okay. So actually, in particular, the external wait call does not. You'll see many cases where the first thing we do when we're told to wait on something is we'll actually call has triggered ourselves to see if we can skip. But here we assume that the caller already tried that. And so we're going to go down the expensive path, which means we take the mutex. And again, this is you saw a similar thing going on in the high-level runtime. We use these scoped lock things to basically safely take a lock and make sure that however we get out of this block, we properly release the lock. So anyway, we take the mutex on the generational event impl, and now it's safe to do tests. In particular, now what we're going to do is we're going to test again whether the event still hasn't triggered, and if it hasn't, then we're going to need to wait on it. If this test fails, then if you see we fall right out, there's no need to wait because while we got around to taking this lock, somebody went and triggered the generation we needed. But if we take the lock and the generation is still not large enough, then we're going to need to have somebody else come in and bump it. So we are going to add to the local waiter list. Remember, that's a list of event waiter objects. And so in particular, if we look up here, one such event is the pthread condition waiter. And the idea here is this is an event waiter that just when the event has triggered will signal a condition variable. And we actually cheat here. What we do is we actually allocate it on our stack since it exists exactly for as long as this function does. We create our waiter, we add it to the list of waiters for the event. And let's not worry about this part right here yet, but we look and we're just going to wait on the condition variable. If you see this condition variable is actually rigged to know about the lock, the mutex for the, where did it go? Oh, you're right. Okay, when we create the gasnet, when we created the condition variable, we use the mutex corresponding to the gen event impl, and so when you wait on a condition variable, there's an atomic, basically, you go to sleep and you atomically release the mutex. And so while we're in this wait call, we've given back the mutex for the gen event impl. Somebody later on will hopefully bump the generation and then go through all the local waiters and call event triggered on it. And so if we are a pthread condition waiter, then we need to reacquire the okay, sorry, this is the lock for the, why is this safe? Oh yeah, okay, we need to reacquire the lock for the generational event so that we can safely signal the condition variable. And so as you'll see, there's a potential for a problem here that you'll see whenever we try to trigger events, we make sure to have let go of all the mutexes before. Otherwise, you get tangled up in double locking mutexes. The other thing is all event triggered methods return a Boolean. And what that Boolean is basically saying whether or not the event waiter object was dynamically allocated. Since the only thing that's holding pointers to the event waiters explicitly is this list of local waiters, typically what we do is we delete those little waiter objects when we call event triggered on them. But there's a number of cases where as an optimization, we'll allocate them on the stack or part of some other data structure. And in that case, you don't want to be calling delete on them. So that's why event triggered takes a Boolean. It says whether or not you actually want to delete the object now. The other thing that event waiters have for debugging purposes is a method that basically prints some information about what it is. This is used in our hang debugging. We basically print out a list of all the events that are still waiting and what things are waiting on them and use it to try to figure out where the loop is in the event graph. But yeah, so basically we took the mutex, we checked to see if we still needed to wait, and if so, we put our condition variable trigger signaler on the list of local waiters, and then we sleep on the condition variable. Sometime later, event triggered will be called, and we'll wake up, and then we know the generation is triggered. We don't need to retest. So that's external waiters, but it shows the idea of enqueuing a waiter. So let's go look now at actually, so this, yeah, I see this was a special case because we got to, we knew that it was needed to do the local waiter. Let's go look at the add waiter call now. Yeah, okay. I want to show you quick an example of add waiter first, and then we will look at the implementation. So, okay, so here is, okay, actually, this is a good example. So we're not going to go into the whole guts of this right now, but this is a request to trigger a generational event. And so one way this happens is if a user event has a trigger method called on it. And just like every other operation in Realm, a request to trigger a user event can actually be made conditioned on some other event to wait on. And so the beginning of the code for triggering an event asks if the precondition, this wait on thing, has triggered. And so remember, this is a lock-free test. It serves two purposes. It always succeeds for the no event. So basically, if there is no precondition, then has triggered is always true, and we jump around it. But if it is a valid event, but we can see without taking a lock that it has triggered, we'll also go around the expensive path. If neither of those is true, then we go through the path of basically we're going to defer this operation, this request to trigger. So we'll build a deferred event trigger object for the gen event, and we will call add waiter to basically tell this generational event impl for the event we're waiting on that we're waiting on whatever generation, and when that generation triggers, we're going to want to perform a deferred event trigger on this particular event. Again, logging messages so we can keep track of who's waiting on what. But now we're going to go look at add waiter. And so the reason I wanted to show you this is I wanted to show that this idiom of, in general, before we ever call add waiter on an object, on an event, we'll almost always ask, has it triggered first? And this does two things. First of all, you can't get the impl of a no event. That will die a horrible death. So if you've been given a no event, has triggered is a convenient way to test both whether you were given a no event, but also whether you were given a valid event, but one that's already known to have triggered in a quick to check way. But if neither of those is true, then generally what you'll do is you'll build some sort of waiter object, and this often involves a dynamic allocation, which is why we like to skip around it. You build a little object that's going to basically, this is a thunk that's going to do whatever we restart this operation whenever the event is triggered, and we're going to add it to the waiter list. And this is where we need to be precise about only adding to the waiter list exactly if the event hasn't already triggered. Otherwise, you wait forever. Let's go see how that works. Gen event impl add waiter. Okay, this is. Let's see, this one isn't too bad. And why is my screen doing this? That's weird. Aye, that was not what I wanted. Come on. Okay, that didn't work at all. No, I'm having a bad user interface day. Okay, there we go. Maybe arrow keys are safer. Okay. Okay, so here is the implementation of add waiter. It luckily fits on the screen. Okay, some more tracing information, which we'll ignore for now. And so there is a potential race here when you're trying to add. We already done a imprecise check to see whether the event has triggered and been told that at least it wasn't triggered when we did that check. But we have to deal with the possible race condition that the event will trigger before, after we've done that check, but before we get around to actually taking the mutex on the event ourselves. So we'll have to keep track of a couple things. One of the things we'll have to keep track of is whether the event did trigger in the meantime. And if so, what we'll do is we'll actually directly trigger the waiter ourselves rather than waiting since it's not going to go on the list. And as you'll see, the other thing we're going to have to do is if we're a remote, if we're not the owner of the event, we may need to subscribe to the event so that we have a chance of actually hearing about the trigger when it occurs. So those are the two things. And this, again, you'll see a pattern of take the lock, make modifications to the data structure itself, but then all the other follow-on actions are typically done outside the lock so that we don't have to deal with double locking of mutexes and such. So the default will be that the event has not triggered and that we're not going to subscribe. We'll go in, we'll take the lock on the gen event. And again, the first thing you do after you take that lock is check to see whether you lost or won the race, depending on how you want to look at it, but basically whether the event has triggered already. If it so the if here is if it hasn't, The else down here is the event happened already. Life is good. We'll just set the trigger now and fall back out of the block that's holding the mutex. If it hasn't triggered, then we need to add ourselves to the list. There's a sanity check here that we're adding ourselves to the correct generation. If you noticed, the gen event impl object, although it describes multiple generations, it has exactly one list of local waiters. And the reason why is that, at least in the non-resilient version of the code, we can maintain a property that there is never more than one generation of wait. There's never more than one generation worth of waiters. We talk about this in one of the papers, but basically, if the owner node always knows which generation is triggered and doesn't reuse an event till it knows that, so it can't have more than one live generation. And if you're on a remote node and you get a request to wait on, say, generation 10, then the fact that generation 10, a handle for generation 10 exists, tells you right off that generations 9 and below have already triggered. So it turns out if you get a request for generation 10 and you see that, and you have waiters on previous generations, you can actually go ahead and trigger them even though you haven't gotten the message from the owner yet. And we'll go look at that function. We've recently refactored this code so that doesn't happen here. That's actually it happens in another place, and we'll go look at it in a moment. But here, this is just testing that this is true. Basically, that we should never be, by the time we get around to trying to wait on an event, we've implicitly know that every generation before that has already triggered, and so we double check that here. This is where we check to see whether we need to subscribe. So if the owner of the event is not my node, and I haven't already subscribed to the event, so this gen subscribed field was keeping track of what subscriptions you've already sent, then what we're going to do is we're going to remember that we've subscribed to this generation now, or that we're about to subscribe to it. We're going to remember a bunch of values from the data structure, because once we let go of the lock, these things might possibly change. But we're going to remember who we're going to subscribe to, and we're going to build the arguments for an active message that we'll dig into next. We won't actually send it yet. We'll send it down below. The other thing we do, whether or not we need to subscribe, is we're going to actually put this waiter that we're trying to add to the list actually on the list, and then we're good. We can let go of the lock. Once we've let go of the lock, we do the 2 checks. If we need to subscribe, this is where we send an event subscription message to the owner of the event. And then the other thing to deal with is if the test here failed, if the event had already triggered, well, then we're going to go ahead and trigger the event waiter. And so we call event triggered on it. And remember, if this returns a Boolean, and if it returns true, then it's asking to be deleted. And so if requested, we will nuke it, and then we return true. So in one incarnation of add waiter, this functionality for triggering it yourself was actually given back to the caller to deal with. And then I guess over time, we just decided to put it here. So it turns out you always, from the caller's perspective, you always succeed in adding the waiter to the list. There's an inherent race in when that thing gets triggered. So even you do have to deal with the possibility that a call to add waiter may trigger the waiter object before the call to add waiter returns. But that's true even if you don't go through this path, right? Even if you go through this path, add it to the list, by the time you let go of the lock, but before you get around to returning, somebody may have triggered the event also. So either way, you have to deal with the case where an add waiter call may actually trigger the object before the call returns, which does mean you have to be a little bit tricky if your waiter object is dynamically allocated, because it may get deleted with this code here or in the callback later on before you get back. So you need to, if you hand a event waiter star into add waiter, then you no longer own it. It may be deleted already. Any questions on that? Okay, let's go look at, maybe we'll go back and look at trigger real quick. And so you can see how this waiter list gets reaped. So gen event trigger, and then after we do this, then we'll go look at active messages and show how these things connect the dots. Okay, so here is gen event impl trigger. Again, like everything else, a gen event impl understands all the generations, so we're explicitly telling it which generation to trigger. We're also telling it who initiated the trigger, right? Because triggers don't necessarily come from the owner. You can create an event on one node and give it to some other node, and it may be the one that triggers it. So you need to keep track of who that was. And then this wait on is for deferral. We already talked about the deferral case. Below here, we can ignore the wait on because it's either didn't exist or it's already triggered at this point. So again, some more logging. And then here is the guts of triggering an event. Again, the same pattern that will have an object, in this case, a vector of event waiters that we're going to wake up. And we're going to do that outside the lock. So we define the data structure here. Then we go in and take the lock. There is a funny race condition. It actually is related to this property of this catch-up property that we'll look at in a moment, where you can actually, in some cases, get two triggers of an event. And so we test here to see if the generation being triggered is already one we knew that was triggered, and if so, well, we don't have to do anything. It's a duplicate message. If it hasn't, then it had better be the next generation. Otherwise, something has gone terribly wrong. If that has passed, then basically we're going to update the generation to the one that's just been triggered. We're going to swap the local waiter list. Basically, we're going to take the contents of the local waiter list and put it in toWake. And since toWake was empty list, this has the also desired effect of restoring local waiters to an empty list. And then, so that's the list of local waiters, and we will notify them below. But there's one other thing we're going to do while holding the lock, and we're going to see whether any messages need to be sent. And this can happen two different ways. If we're the owner of the event, then it's up to us, when a generational event triggers, to notify any remote waiters that that the event has triggered. And so we're going to build this event trigger object, arguments, and we're going to send out who triggered, what event was triggered, and then we're going to get our list of remote waiters that we're going to have to send to. So this is going to be a bit mask of which nodes to send to. This comment is actually no longer valid. It used to be you couldn't actually clear one of these things. So this is me reinitializing it. But now you can actually just call clear on a node mask to clear out the list of waiters. And the idea here is that in the case of generational events, you can basically only have subscribed to the most recent generation because you know everything else is triggered. So basically, once I send you a message, then that clears that subscription. And if you decide you want to subscribe to a future generation, you'll send another message and set the bit back. So here's that node mask, and here is sending a bunch of messages. This loop here should technically be outside the lock. This is a performance problem. I don't know why it's inside the lock, mostly because it's hard to debug performance issues on these sorts of things. But I've actually fixed this in the resilience version. So like I said, in most cases, events should be being sent outside the mutex rather than inside here. But here's where we iterate over all of the bits in the node mask and send trigger messages to anybody who cared. And then the other case is that if we are not the owner of the event, or like I said, any node can trigger an event if it completes the operation corresponding to it. And so if the trigger node, so this is if we're not the owner, then there's actually two different cases here. Either we triggered it locally and we need to send a message to the owner of the event to say that it's triggered, or we have just received a message from the owner and we'd better not send another message because that would cause loops. And so if we are the original triggerer of the event, so if trigger node is equal to my node, then we're going to send a trigger message to the owner. And actually, you see this is actually the same message that's used both for the owner to notify remote waiters, but also for a remote trigger to notify the owner. And that's why we send information saying which node actually triggered. Actually, I guess the one thing I should point out here is that we're careful not to send a trigger message. In the case where a remote node triggered it and sent a message using this path, then on the owner node, when we go through this path, we're careful not to send another message back to the node that triggered it. There's no point because it knows it already triggered. Once we've sent our messages, and again, both of these should be outside this mutex, then we're going to do two more things. If we are the owner of the event, then we know that this generational event can now be reused because it's in the triggered state. So this is us adding it back onto the free list so that a call to create gen event later on will be able to reuse it. And we had that list of that wake list of any event waiter stars that were queued up waiting for this generation to trigger. And so now we'll iterate over that list and we will call event triggered on it. And if they request to be deleted, then we will delete them. That we're doing on time. Okay. So that is basically the functionality for generational events. We keep a list of local waiters. We keep two monotonically increasing variables, one for what generations are known to have triggered and what generations are known to have been subscribed to. Let me show real quick that fun special case related to remote events. This is the catch-up code. So the idea here is that whenever you ask for a generational event, so this is where we have an event E and we're asking for the implementation for it. This is the case here where basically the mere act of asking for the generational event for generation 10 of something is implicitly saying that generations 9 and earlier have triggered. And so we do handle that case here in this check for catch-up. And so you see we're passing the generation one less than the current one. And so if we go look there, then what this code is doing is basically, so we call this with the implied trigger gen. So we haven't actually received a trigger message yet, but if we're asking for generation 10, then generation 9 must have triggered. So this looks a little bit like the triggered method in that we're going to keep a list of event waiters to trigger. We're going to take the mutex. We are going to double check that, again, that there wasn't a race and we didn't already trigger this list. And then we'll do a quick sanity check. This catch-up can only occur on remote nodes. But if it does, then we will bump the generation to the implied generation and again do the same thing. We'll swap the list out so that we can release the lock and then trigger the waiters here. There's no messages sent in this case because we assume that any messages are already in flight. And that's actually how you get that double trigger case. If this check for catch-up thing fires while the message about the trigger is in flight from the owner, that's how you get the double trigger. So this has a property that basically this assignment here basically guarantees that property we checked earlier, that if you're holding a generational event impl, then the generation field in it must either be the past the generation if additional triggers come in, or it must be the one immediately before the generation you're interested in. It can never be older than n-1. And that's why we only have to keep one list of local waiters. Unfortunately, this cool optimization goes out the window once you turn on resilience, which is too bad. But that's what the current version of the code looks like. Okay, so now let's go look at the event trigger message. So that'll be our first active message. And again, this user interface is annoying. Okay, so event trigger message. Okay, so this stuff that we're going to look at now for the rest of today's hour is going to be basically some wrapper goo around the horrible ugliness that is GasNet active messages. I'm actually not going to show you what GasNet active messages look like. You can inflict that pain on yourself if you wish in the future. But I'm actually working on some code to further hide it so that hopefully future generations don't have to deal with it at all. So I will show you simply how we use them, and if you're ever curious about why they work or why they occasionally don't work, then you can dig into the guts of ActiveMessage.h and ActiveMessage.cc. Anyway, if you want an active message, you have to do a couple things. First of all, you're going to need a unique message ID, which will identify the message, and let's go find that first. Event trigger message ID. So basically, we have a bunch of active message IDs. GasNet requires that you start at 128. I gave myself a little margin, so all the realm active messages start actually at 140, and they're just consecutive IDs. And their values are irrelevant as long as you don't have any duplicate values used. Okay, so you need a message ID first. The next thing you need is a structure that defines what are the arguments to the message. And so as we saw for an event trigger, there's actually only two things we need to send. We need to send what node did the triggering and what is the event being triggered. So remember, this includes both the ID and the generation. So we define that structure. We also need to define a handler. And for what are called short active messages, your handler is just a void method, a void static function that takes one of these args structures as the arguments. And so now that we have our ID, our argument data structure, and our handler, we roll those up using the wonderful power of templates into a message type. And this is basically going to give us the way to refer to this message in a not quite so insane way. And so there's a couple different kinds of messages. In fact, there's, I think, 3 that we use. The most common one we use is this active message short no reply. And what that means is it's a message where the data consists only of this structure, only of the structure you provide. There's no variable data with it, and there's no reply. It's a unidirectional message. And so we'll look at the other 2 cases in a moment, but this is the simplest one. And so to do this, so now let's go look at where event trigger message gets used. So one way that it gets used is it has a static request method. And so this is how you actually send a message. You build the data structure that you want. So remember, there are trigger args. So here we're filling in the node. And right, this is the case where we are. This is a funny case. Let me not worry about that one right now. Let me go find the actual. Here's the trigger code. Okay, so here's a case where let's do the case where we're sending a message that the event has triggered. So we will set the node to the trigger node. We will fill in the event with who we want, and this is us sending a message to the owner of the event, and we pass the arguments in. Similar thing happens here for we're sending to all the remote nodes that we're interested in. We again build this one data structure here, and then we just send that set of arguments to every node that's lit up in this send mask. Okay, so that is how it gets used. You basically build this data structure, and then you just call request on it. You say which node you want to send it to, and since it's a short message, all we have to do is provide the arguments that you want to send. The other thing you have to do if you create a new kind of message is you have to register it with GasNet. And there's a few hoops to jump through here, but basically we build when you start up GasNet, you give it a list of handlers, and the handlers are associated with basically message IDs and function pointers. Those templates that we saw above, the active message short no reply template provides a helper function that's going to take care of that for us. So you just need to make sure you call the add handler entries on each message type you create. And basically the pattern here is it's filling in this handler list. It passes back how many it added, and so you can just keep bumping this, and we have a debug string that says what to do. If you forget to do this, you'll get a friendly message from GasNet saying it received a message that it didn't have a handler for, and the world will end. Luckily, you only have to do that usually exactly once for each new message you add, and so you do that here. Okay, so those are basically the two methods that exist on one of these types is the ability to send a request and the ability to register the handlers with GasNet. The one other thing we have to go do now is look at the usage of look at the I lost it already. I want to go look at the implementation of handle trigger event or handle event trigger. Come on. Okay, so here is this. One little annoying thing about this particular design pattern, and I'm trying to fix it with the modified version I told you I was working on, is that These methods have to be static methods. And just because of the way it's done, they're typically outside the class that is going to implement the functionality. And so that's why, at least in Realm right now, you'll see that nearly all the member variables of the classes in Realm are all public, because I got tired of fighting it. Anyway, so here is handle event trigger. So we're getting our argument object. And remember, it had a node in it and the event we want to trigger. So we'll fish out the event from the args and use that to get the generational event impl. And then we will call that trigger method on with the corresponding generation and let it know who was triggering it, so we know which path we're on through that trigger code. So most of the message handler functions like this are about this simple. Basically, the arguments object has to use handles because it's going between nodes. So typically the pattern you'll see is for each handle in the arguments, we will get the corresponding implementation, and then we will call a method on that implementation and give it the other arguments that it needs. So any questions on active messages? It basically looks like a remote procedure call. I'll use the last couple minutes to show the two other kinds of active messages, but if there's any basic questions about what a short message looks like, it's good to do that now. No? Okay. Let's go find a more complicated one. Let's go look at it in active message medium, no reply. So this gets used in a bunch of places too. It has a very similar pattern to a short message, except that a medium message, in addition to the arguments object, is allowed to pass a blob of data, a variable size blob of data. And so you see that first in the handler. So in addition to taking the arguments for the message, it's also going to get a void star and a message size. There's one quirk of this interface with GasNet that your arguments, basically we need to stuff some other arguments into your structure. And so if you're a medium message, you have to inherit your arguments structure from the base medium object, which basically gives us a few fields to play with. One thing I should mention here is there's a limit in GasNet that your argument data structure can be no larger than 128 bytes. And that actually includes the, I think, 16 or maybe even 32 bytes now that this base medium object is chewing up. So it's actually not unusual to find that for some larger messages that you go over the limit. Right now, you have to stand on your head and do silly things to avoid that. The newer version that I'm working on will actually eliminate that requirement. But so anyway, medium message looks a lot like this so far. We're going to build arguments. Our handler is going to take a data and a data len, and data is not owned by you. This data is owned by GasNet, so you need to use it immediately. By the time you return from your handler, this data gets nuked. So if you need to make a copy of it, you have to do it before you return. You register it the same way, right? We use this type def, this template to build a message object, and then we call add handlers below. And then let's go look where this is. Actually, it's called right here. So when you do a request for a medium object, again, you give it the node that you want to send to. You give it the argument data structure for the fixed length arguments. But then you have to give it data as well. And you actually pass three things to it. You pass a pointer to the data. You pass its size. And then you also have to pass one more field, which is it's called the payload mode. And let's go look at activemessage.h, and you can see the different modes. And this is basically an optimization to try to avoid copies when we can get away with it for these variable size payloads. So I mentioned activemessage.h is a nasty, horrible blob of code related to GasNet. I'm not going to go through much of it. I am going to just look at near the top this list of payload modes. So there's a bunch of different kinds of payload modes that you can send, and they're used in different cases. None is a special one where you're actually sending a zero size payload. Medium messages can take the size of payload you send can be zero size, and if you send none there, that's an indication that you're intentionally not sending data. The one that gets used a lot for the DMA code is keep. And what keep means is that the pointer you're passing is for data that will be valid basically until the message is handled. And so in particular, if you're doing a remote DMA, usually the data, the source data is in some instance somewhere, and you know it's not going to change until the event, the finish event for that DMA triggers, and some other operation goes and overwrites it. But until that event triggers, you know that nobody can overwrite the data, so there's no point in making a copy of it. And so you pass a pointer into the active message code, and you say keep, and what that means is a copy usually won't be made. It's guaranteed to be stable until at least until that message is delivered to the other side. The other one that you saw in the code below is the opposite of it. Copy is saying to the active message code that the pointer that's being passed in is temporary, and in particular, if the active message code is not going to immediately pass it on, is not going to consume it before returning from the active message request call, then it needs to make a copy of it. And so you'll typically use this for something you've built on your stack or something that you intend to change quickly. If it's something you yourself dynamically allocated, then you actually use payload free. And the idea here is this is actually passing off ownership of that dynamic allocation to the active message code. And so it doesn't have to make a copy. And if it's not going to use it right away, it just holds onto the pointer. And when it's done with it, it knows it's going to call free on the data. There are a few other things here, which actually, so these are the 4 that you actually used if you're a caller, if you're a requester of an active message. The internal code keeps some other state related to the state of the payload as it gets copied or not through the system. But the main 4 you need to worry about are these 4 up here. So either you have no payload, or you have existing data that is stable and can be just used by the active message code whenever it's ready to do so, or you've dynamically allocated a copy and you want the active message code to free it when it's done, or you've put something on your stack or in some other thing that you're going to overwrite, and so you really want the active message code to make a copy right away if it needs to. And like I said, the rest of this horrible goo in here, you can look at if you're masochistic. It's a combination of gasnet scariness and template scariness and preprocessor macros. So I would recommend only looking at it if you're enjoy pain. I think I've got only 3 minutes left, so I'm going to stop here for today. My next thing will be probably looking at processors and tasks, and I guess I'm up again in 2 weeks. But with the last couple minutes, if anybody wants to ask questions, now would be a great time to do so. Okay, I guess people are either understanding or just terribly, terribly confused, but either way, questions can be asked offline later on as well. And Elliot can press the red button again, and we will call this session to a close. Talk to you all next time, guys.